Hey, good morning, everybody. This is Mr. Ainsworth in here, and we're going to follow up and do the second half of our lesson here in Section 2, Unit 2, Section 2, dealing with zeros and x-intercepts and talking about multiplicity of a function here. So let's just do a little review here. We talked about in our first example, we have a g of x here in factored form, and we talked about how to find its roots or zeros by setting each factor equal to 0. And take a look at the graph. We're using Desmos here and analyzing a few functions and taking a look at the degree and the roots and things of that nature. And so if you just take a look at this different example here of Desmos here, notice that I have a function y equals x minus 1 to the second power times x plus 2. You'll notice here that it intersects the x-axis at negative 2. That's an x-intercept or a root of the function, commonly known as a zero of the function because we're on the x-axis. And notice that the function crosses the x-axis at negative 2. Why? Because the factor here, your x plus 2, only appears once. And we say that the multiplicity is 1 because it appears once. Or you can think of it as the degree of the factor, which is the exponent up there. And then notice that we have a bounce at 1, okay? And it hits the function hits the x-axis and bounces off on the same side. We call that a bounce at 1. And the reason why is because the multiplicity is 2, or the degree of that factor, x minus 1, is raised to the second power. So it's degree 2, which is even. So even powers like 2, 4, 6, 8 produce a bounce, and odd powers like 1, 3, 5, 9 produce a crossing. Okay, and it either sharply crosses through the x-axis like at negative 2 here when the degree is 1. But if the degree is like 3, 5, 7, and 9, any higher power other than 1, like this other one here, you'll notice that we have a different thing happening. We have a bounce at 4 because the even power, or we say the multiplicity is 2. And then we have on the other side over here at negative 3, we have a crossing, but notice that it's a gradual or smooth crossing, not a sharp crossing, because the degree is 3. And that always happens when the degree is higher than 3, 3 or higher. If it was 1, there'd be a sharp crossing, but if the degree is anything higher than 1, but it's odd, like 3, 5, 7, 9, etc., we have a gradual and smooth, shallow crossing through the x-axis, okay? So that's called the multiplicity or the degree of the function. So let's kind of like summarize it here in the learning targets. And this is the part that I didn't get to in class. And let's just summarize it. Okay, so we have our first learning target. All right, deals with the multiplicity of the function. Okay, so multiplicity. Fancy word for a simple concept. Okay, we're going to refer to that as K. All right, and there's two ways to think about it. So the multiplicity could be the number of times the factor appears. You can think of it that way because we discussed that in class. Number of times a factor appears. I'll talk about that, and I'll give you an example in just a moment here. I have to write it down. Or you can think of it as the degree of the factor. Okay, the degree of the factor. Okay, so what do I mean? So let me exemplify. All right, so here we go. Let's say we take x minus 2 to the third power. Okay, so very simple example there. So notice that here k is 3. Okay, notice that it's odd. Okay, so we refer to as the multiplicity here is 3. Okay, so here the factor is 2. So we have a 0 at 2. So at x is equal to 2, we have a multiplicity. Okay, just use MULT for multiplicity, equal to, y2. The multiplicity of 3, because it's raised to the third power here. And because it's odd, we can say that we have a crossing at that point. Okay, it goes through the x-axis. Okay, it goes through the x-axis. Now, if we have something else, if we have something like this, we have x, let's say plus 1 raised to the fourth power. Okay, here k is 4. So k, the exponent, the degree, is 4, and it's even. Okay, so at your 0, which is negative 1 in this case, at negative 1, we have a bounce, okay? And you can verify that with decimals any day of the week because we've done that in class. Really easy to do. You just type the function in, look at it, and you can see that you have a bounce at -1. All right, and that's the only thing you need to really think about when you're given a function in factor form. Look at the degree of the factor, which gives you information about the root, which we call the x-intercept. Let's put this down. So the x-intercept here, there's another name called root of the function, which is the zero of the function. Okay, so these names are used interchangeably depending on the context of the situation. All right, so now next thing we have is general factored form. So next learning target, LT number 2. All right, general factored form. General factored form. This is a really cool form. Really, really nice to have this form right here. And you saw it in example 1. Okay, right here, g of x, that's factored form. In fact, you saw it in f of x here, example 2. And you saw it in example 3. Actually, you saw it throughout the entire lesson. Okay, but in general, okay, we say general factored form looks like this. So f of x looks like some lead coefficient a could be positive or negative, times x minus r1, where r1 is a root, times x minus r2, where r2 is another root, times x minus r3, the third root. And this, polynomial can have n roots if it's nth degree, okay, all the way to x minus r sub n, where these r1, okay, r1, r2, and r3 all the way up to the r sub n, okay, are roots of the function, okay. So, and a here is called a lead coefficient. So let's make a little note of that. So this is called a lead coefficient, okay, and your roots here, which are the zeros of the function here, are R1, okay, R2, R3, as many as there are R sub n, okay, if it's nth degree. And there we go. And then when you want to find your zeros, you just set x minus r1 equal to 0 and find your roots, or your zeros of the function. All right, so let's apply it a little bit here. Let's go into your check for understanding. This is section 2 here. And the graph of the 6th degree, look at this. We've got a 6th degree polynomial here is shown. This is g of x, okay, as stated in the directions. And it says identify the zeros, okay, the zeros of g and state their multiplicity, okay. And again, we're going to look at the degree of the function. All right, so here we have r1 here is -3. Okay, so we have a root at -3. We also have a root, a second root at 2, and then we have a third root at 4. So we have 3 roots, 3 real roots. Okay, now it says 6th degree. So what in the world is going on here? Okay, so at -3 here we have a bounce. And what that means is it's got to be degree 2. It has to be even degree. Even degree. So what does that mean? Well, 2, 4, 6, 8, or so on. So the minimum degree there would be 2. So that's my first observation here. So at x equals -3, okay, we have a multiplicity. Again, the multiplicity is the degree. Okay, multiplicity is 2. Why? Because it's got a bounce, so it has to have an even degree. All right, so it could be degree 4 too. That's possible. All right, that's why it says, well, in this case, it has to be 2 because we have some other roots here as well. So we have a crossing at 2, and then we have a crossing at 4. Okay, so which one's degree 1 and which one's degree 3? So here we have a shallow crossing. So this is a shallow, or what's called a gradual crossing at 2. Okay, so that means we have an odd degree. Okay, but it's not going to be degree 1. It has to be greater than 1 because we have a sharp crossing here at 4. Okay, sharp crossing, that means it's odd degree, but it has to be 1. So odd degree 1, and then the other one at 2. We have a shallow crossing at 2, so it has to be degree 3. It's got to be odd, but it's either If you have a sharp crossing, always degree 1. And then the other one, if you have a shallow one, it's got to be higher than 1, but it's still odd, so it's got to be 3. And if you add up the degrees here, okay, so the degree at -3 is 2, and then we have a degree 3, and then we have degree 1, okay, 2 plus 3 plus 1. Guess what? That's 6th degree. Okay, so let's state that. So on the other one here, we have at 2, so at x equals 2, all right, multiplicity, what did I say? So multiplicity is 3, okay, and then at 4, okay, running out of room here. So at x equals 4, we have multiplicity of 1 because there's a sharp crossing. Okay, so this is just repeated myself a little bit there, but you got the idea. Okay, part B, does the equation g of x have any imaginary solutions? How do you know? Okay, so we add up the degrees. Okay, so sum the degrees. Okay, and degree 2 plus degree 3 plus degree 1, and we get 6th degree here, which is the degree of the polynomial, so equals the degree of the polynomial. And if they said we had like maybe an 8th degree polynomial, then we would have imaginary solutions here. So since the degree or the sum of the degrees equals the degree of the polynomial, we're going to say no imaginary solutions. Okay, so no imaginary soluciones. Okay, we'll see some cases later on where we have some, but since the sum of all those degrees equals the degree of the polynomial, which was given, okay, right at the very top, we have a 6th degree. We do not have any imaginary solutions. If we did have some, it wouldn't be degree 6, it would be degree 8, okay, or 10, or something higher than 6. All right, number 2. Number 2, what does it say? A polynomial has zeros at 4 with a multiplicity of 2. Okay, and we have x equals -2 and x equals 3i. What is the minimum degree? So keyword minimum. So right there, we have to understand that if we're given an imaginary solution, which we are, okay, like x equals 3i, so this is called an imaginary solution. Okay, x equals 3i. It automatically tells us that the conjugate x equals -3i is also a root. Why? Okay, why? The answer to that is because complex solutions or complex roots, or what we say imaginary roots, always come in conjugate pairs. Okay, so complex roots, which are called imaginary, they're imaginary here. Imaginary roots always come in conjugate pairs. Always come in what are called conjugates. So let's focus on our new word here, conjugate pairs. Now, what are conjugate pairs? Well, in Algebra 2, you guys know that the general form of a complex number is a plus bi, and its conjugate is a minus bi. Okay, these are called conjugate pairs. So in our example here that we just went over here, they gave you 3i as a root. Okay, that means -3i is also a root. Okay, just change the sign of the imaginary part. Let's make a little caveat here. Okay, so change the sign, okay, of only the imaginary part. Okay, and then it says write an equation in factored form. So there you go. Here's where your factored form comes in. So at the very top of the screen, we have general factored form. What you want to do is take this factored form here that we have, and you want to apply it to this one right here, general factored form. So let's go for it here. We've got the roots, and let's write it here. So f of x, okay. So f of x is going to be equal to some lead coefficient a, all right, times x minus 4. Now it says a multiplicity of 2, so times x minus 4. It's a double root. All right, times x minus a negative 2. You always subtract the root. If you look at the form, it says x minus r1 times x minus r2, etc. It's always a subtraction, and then you simplify the result when you're done. So I'll simplify that when we're done. And then x minus 3i times x minus a negative 3i. Okay? Now you simplify, and so you get a times x minus 4 to the second power. Again, these two, x minus 4 times x minus 4 is x minus 4 to the second power. All right, and then times x plus 2 because we have a double negative. And then here you keep it the same. So x minus 3i times x plus 3i. So simplify, all right, simplify when possible. So again, what I did, let me just be more specific. Your x minus a negative 2 becomes x plus 2. Your x minus a negative 3i becomes x plus 3i. You just simplify. And when you see double negatives, you guys know in pre-calc that that's a positive, okay? All right, and you have what's called general factored form right there. All right, next one, what do we have? F of x equals x plus 6 times the quantity x squared plus 2x plus 5. So we got multiplied by that trinomial there. It says find the zeros. So when you find zeros, you set the function equal to 0. Set f of x equal to 0 and solve. That's an algebra 1 technique, basic skill. Right here, so let's do this here. So we're going to have x plus 6 is equal to 0. When you set the function equal to 0, the factors could either one could be equal to 0. So you set both equal to 0 and solve. All right, so here, obviously, x equals negative 6. There's our first root. And then here, x squared plus 2x plus 5. When is that equal to 0? Well, guess what, guys? That's not factorable. I don't know two numbers that multiply to 5 and add to 2. Okay, so it's not factorable. So we have to use the quadratic formula. Okay, so we're going to have to go off to the side here. So here, the A value is 1, B is 2, C is 5, and we have to use the quadratic formula here from Algebra 1. Quadratic formula. So let's review that. So x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So let's get started. Here we go. So we have the opposite of b, which is negative 2, plus or minus the square root of b squared. So you square 2 and you get 4, minus 4 times a, which is 1, times c, all divided by 2 times whatever a is. So let's go off to the side here and let's work this out. So negative 2 plus or minus the square root of 4 minus 20 divided by 2. Okay, and we have negative 2 plus or minus the square root. Ooh, getting a little carried away there. The square root of negative 16, all divided by 2. That gives you negative 2 plus or minus 4i, all divided by 2. And then you divide them both by 2. All right, you got to divide both numbers by 2. So you get negative 1 plus or minus 2i as your roots. Okay, so the roots, look, there are two of them, right? Okay, the first one is negative 1 plus 2i, and then the second one is negative 1 minus 2i. So minus 2i. So you have two roots. Okay, and then it says write your equation in fully factored form, which is what we just did earlier. Although your roots look like binomials, so it's a little bit more complicated. So here we go. So f of x is equal to, so a times x plus 6, that's already factored, okay? Actually, you don't need to put the a there, so let me take that out. You just have to factor your trinomial, okay? So it looks like x minus the first one, so put in parentheses, minus or negative 1 plus 2i, all right, times x minus the second one, and you put the roots in parentheses because they're binomials, guys. All right, so first one, second one. So it's going to be, negative 1 minus 2i. So negative 1 minus 2i. And again, you put them in parentheses. So again, your general factored form is x minus r1 times x minus r2 times x minus r3. And again, these are called roots. Okay? And there we go. So this is, obviously a third degree function. It's a cubic. Okay? Why a cubic? Well, it's third degree. Okay, and there you go. Those are all the skills needed in your homework here, and the only thing you need to do is get good, right? Because that was some algebra right there. That's all Algebra 1 and Algebra 2 review, all right? Well, Algebra 1 for most of it, and then Algebra 2 on the second part of it. All right, and that is all the key ideas in Section 2. So obviously, let's go into your homework right here. All right, Section 2 homework. Section 2 homework here. Give it your best shot. Work in groups. Use my videos if you need it, okay, because there's a video resource for everything in this class. And do your best, and I will see you when I get back. Take care, guys. Bye-bye.